Okay, so I'm going to keep talking about pre-processing EEG data, and in particular using independent components analysis to isolate and remove sources of noise in EEG data. This is continuing along with our pre-processing stream. So previously we talked about this. Last video was all about trial rejection, and now we're going to talk about ICA. So running the independent components analysis on your EEG data can take a long time depending on how many channels you have and how much data you have. It can take several or many hours per subject. So generally I would have a separate MATLAB script or maybe just a separate piece of a different MATLAB script. But this would be something that can run through, it can loop over subjects, import each subject's EEG data, run an ICA and save the weights, and then move on to the next subject. Something that can run, for tens of hours or days on end without any user intervention. And again, this is part of the thing that takes a long time and is meticulous, but you only have to do it once. So once you run the ICA on a data set, unless you want to change something you did back here, you won't ever need to rerun the ICA function. It's another good reason why you want to make sure that you're doing these previous steps very carefully, so you don't need to redo these, because if you need to redo these, you also need to rerun the ICA. It's not the end of the world, of course, but it will cost some time. Okay, so what is independent components analysis? The kind of classic explanation of the problem that ICA was, or blind source separation methods like ICA were developed to solve, is identifying individual sources in a crowd of noise or of other additional sources. So you can imagine if there are two speakers in a room, and then there's some ambient noise, there's a crowd of people talking, businessmen singing or whatever these guys are doing, birds chirping outside, all sorts of things. If you only had one speaker or one microphone, it would be very difficult to isolate an individual speaker, because that one microphone is going to be recording signals from multiple sources. But it turns out that if you have multiple microphones that are placed in different places around the room, they can be used to isolate the sources or different sources of, in this case, auditory information. Quick note here, on the sunny side of the Atlantic Ocean, people tend to call this analysis ICA. I don't know why they say that here, but they tend to say ICA. In the US, they tend to say ICA, so it's just minor culture difference that you should be aware of depending on which side of the ocean you're on. So taking this idea of identifying speakers amongst all these other sources of auditory signals to the brain, the idea of ICA for EEG data is that there are multiple independent sources of activity in the brain. There's brain activity, there's eye movement, so it's other sources that contribute to the signal in EEG that are not even coming from the brain, muscle artifacts, all sorts of different brain visual dynamics, motor dynamics, everything in between. Now, if we only had one electrode on the head, it would be extremely difficult to isolate these different sources. But because we have many electrodes, tens, dozens of electrodes, or sometimes a few hundreds of electrodes, it's possible to use blind source separation algorithms like ICA to try and isolate these different sources of variance. And the idea is that it finds statistically independent sources of variance in the EEG data. In this video, I'm not going to go through any math or anything like that, just sort of talk about it more conceptually. ICA is very good for identifying artifacts due to independent sources. And one of the main ones that people use it for is blink artifacts, to subtract the blink and other eye movement related artifacts from the data. Here's another, I think this picture is taken from the EEG Lab website, as is this one. So this is another picture illustrating what you get from ICA. So what you get from, or the result of the independent components analysis is a set of weights for all the electrodes. And the idea is that the weighted sum of all the electrode activity is some independent source. So each component has one time course, and each component has n electrodes. So in the sample data set that I often use, we have 64 electrodes. So each component has 64 weights. And when you take the weighted sum of the activity at all electrodes, you get a single time course. So each component has one time course and 64 weights, or however many electrodes you have. Yeah, so there are two different ways that people use independent components analysis in the literature. The most frequently used approach to take with the ICA is to use the ICA to identify sources of noise and subtract the noise from the data as a way of pre-processing the data. And that's what I'll show you here. Another way that people use independent components analysis is to analyze the components instead of analyzing the channel data, the sensor data. So that's fine. There's sort of some minor philosophical differences that would lead you towards analyzing the components versus using the components to identify and remove sources of noise, and then analyzing the channel data. Once you get the time series, any of the other kinds of time frequency analyses that I've discussed in previous lectures can be applied either way to the components or to the channel data. Okay, so once the ICA is run, then you will want to identify and remove these bad components, these artifact components. And that's what I'm going to spend the rest of this lecture on. So identifying and removing artifact components it's a little bit of an art, and it's also, there is a little bit of subjectivity. It's similar to we could have a similar discussion to why you would do manual trial rejection instead of automatic trial rejection. So I'm going to illustrate to you the way that I do ICA for removing artifacts from the data. But this is in no way to suggest that this is the only way to do it, or the only correct way to do it, or even the best way to do it. It's just the way that I do it, the way that seems to have worked well for my applications, my situation in the past. So here's our EEG Lab GUI. And so what I do is I like to look at the components and also look at the component time courses at the same time on the same screen. I'll show you, after we walk through this a bit, I'll show you this in MATLAB. So here we have the component time courses. So each one of these corresponds to the weighted combination of each one of these. And these are the maps. So here, one of the most prominent components that you can always identify is the iBlink component. So here you see it's component 3. We know it's component 3 because of the very anterior distribution of weights. And if you look at the time course, there's not a whole lot of stuff happening here. And then we see this really big, basically blink. This is the representation of the blink in the EEG data. And then you can see other things. So here, component 13 looks suspicious. Looks like there's a lot of EMG noise on here. And we can see also here, it's mainly just driven by, or this component is really just driven by one electrode. So, the question is, which components do I remove? Which components should you identify and isolate from the data? The answer is seemingly simple, and it is that you should remove the components that contain noise that is not caused by, this is actually wrong, it should say brain dynamics. You want to identify noise that is not caused by brain dynamics. So that's like eye movements and EMG, so muscle activity, maybe EKG, heart rate, heartbeat related artifacts. These are actually real EEG dynamics, but they're not generated by signals in the brain that we want to care about. So that seems very easy. In practice, it's unfortunately a bit difficult to know exactly which components to remove. So I think when you're looking through the components and trying to identify which ones to remove, your null hypothesis, so the way you approach this should be that all of the components are accepted except for one, and that one component that you will always look for to reject will be the eye blink component, the oculomotor artifact component. And you should need very strong, very compelling evidence to reject the null hypothesis, which means that you need to really, really convince yourself that you should remove more than one component, more than just the blink component. The reason why this is the case is that most often the components are mixed with signal and noise. So the ICA is generally not perfect at really nicely separating the noise from the signal. So most of the time you will see components that contain something that looks like real brain signal and also something that looks like noise. And so this is where things get tricky. So here's some examples. Here's a clear eye blink component. You have a very anterior distribution of the weights. You can see when you look at the so this is like a ERP image, I think they call this. So each line here corresponds to a trial, and the color corresponds to the amplitude of the single trial component time course. So here you see that there are these sparse, very large amplitude dynamics, and these are the blinks. So here is where the subject blinked, here, 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 here. So here you see all the blinks. When you look at the time course, it's not really very task related, in the sense that you don't see a very sharp ERP, basically a sharp evoked phase locked response to time zero. So this is definitely a component that you should feel very comfortable removing from the data. Here's another example of blink with a different electrode montage, I guess. I think a different experiment must be. Here you see the blinks here. They are a bit time locked, so probably this experiment was pretty fast, and this was probably when the trial ended around here, so the subjects tended to blink after the trial ended during the intertrial interval. So again, this is something that you should feel very comfortable removing from your data. Here's another example of a component where it's driven by noise. So I look for a few things when I look at these component windows. You want to look at the topography, and if the topography is driven by a single electrode, like this, the weights here are basically all zero, and then the entire component is driven by one electrode. So this arouses suspicion. It doesn't necessarily mean that I will remove this component, but it does make me suspicious enough to look into it more deeply. And then here in this ERP image, and also in the ERP, in the time domain average response, you don't see much of a task-related response, So one thing you can ask yourself is, imagine this black line were not here, this vertical line were not here. Would you know where time zero was? Would you know where trial onset was? And in this case, you wouldn't. You would have no idea where to put time zero. It could be here or here. And you'll see that when you look at components that contain real task-related brain activity, you know exactly where time zero is without having to see this vertical bar. The other thing I look at is the power spectrum. So here, you should, if this is real brain activity that's driving the EEG, you should see like this kind of characteristic 1/f shape, maybe with some little bump at alpha or theta or something like that. And what you see here is that the power spectrum very quickly drops and then comes back up again. And this is characteristic of muscle activity, of EMG artifact. It's not characteristic of real brain dynamics. So I would also feel pretty comfortable removing this component from the data. Here's one of my favorite expressions. When there is doubt, there is no doubt. If you're not really confident about whether you should remove a component, you probably should not remove that component. So if you're doubting whether to remove a component, then there's no doubt that you should leave that component in the data. So now we get to more difficult examples. So here we see this component is driven mainly by one electrode, so this looks suspicious. But if we zoom in to this, this evoked response here, then we see that there's a very strong ERP. So you would know, or you would have a pretty decent guess of where to put time zero just by looking at this plot. And you see from the power spectrum that it has a bit of a kind of normal looking EEG shape. There's a little shoulder here at theta and another shoulder here at, like, I don't know, low beta or something. But clearly there is noise in this component. But this is one of these components, actually like most components, that have a mix of signal and noise. And so I would not remove this component because on the one hand, you will be removing some noise from the data, but you'll also be removing some signal from the data. Furthermore, if your experiment, if you're not really focused on this electrode in your analyses, you don't really have to worry too much about a moderate amount of noise being on here. If you're focused on like posterior things or midfrontal things, and you don't really need to worry too much about some noise being on these very lateral electrodes. Here's another example of a component. So here's something that looks suspicious initially because the entire component is basically driven by one electrode, so that makes me a little bit suspicious. But you look at the time course and it's very clear that there is a very beautiful time domain ERP response here. So, and if you didn't see this vertical bar, you would know exactly where time zero was in this experiment. You would know exactly that there's something happening here that elicits some kind of a response. So again, this is a component that mixes signal and noise, but I definitely would not remove this component. You're going to be removing real brain signal, which you don't want to do. Let's see, here's another example. So this one gets a little bit trickier now. So we see this one has kind of a characteristic muscle EEMG artifact property. So it's mainly driven by one electrode and it's sort of on the face basically. So you can see there's a lot of noise in this component. You do also see something that looks like a pretty clear task-related response. This power spectrum shows a big EMG response. But another thing to keep in mind is that these components are numbered. They're ordered in terms of how much variance they account for in the data. And so in this case, we have 64 electrodes. And so component 30 means this, component number 30 means that this component is actually accounting for very little variance in the data. So it might look really awful and prominent when you see this component isolated, but in fact, this component is not really accounting for a lot of variance in the data. So usually I don't even remove components after after the first 20 or so, because I mostly just ignore them unless they seem to be particularly awful, just because it's not going to make much of a difference either way. My philosophy is it's better to leave in a little noise than to remove real signal. This is something that people struggle with when they first start doing EEG analyses, particularly if you're coming from some other field where you have less noisy measurements. And so I think it's important to realize EEG data are not really horribly, awfully noisy measurements, but they are kind of noisy. There is some noise in the data, and you will never be able to get rid of it. And this is part of the reason why you collect lots and lots of trials in your experiment rather than just collecting 3 trials. So it's important to realize that there is noise in the data, and you should not go into ICA cleaning or any pre-processing step thinking that you will be able to get rid of all the noise. If you have that mindset, you're going to end up getting rid of a lot of real signal, which you don't want to do. So you should really only remove components when you think that they're really just noise and there's no signal in there. Okay, so after you've identified components to reject, and I'll show you this in MATLAB in a minute. You can do in EEG Lab, you can sort of identify these components to remove. And then there's this nice feature in EEG Lab where it will allow you to, or it will plot for you the data before and after removing those components. So here you see in this dark blue color, this is the original EEG data, and in red, this is the new EEG data after removing the components. The most obvious difference is this really large peak. This is the blink artifact. And you see that the red, so the data after removing the component, it's very nice. It's very clear that the blink artifact has been removed from the data. Here you see this other kind of slow drift here. And what you want to see in the data after removing these components is that the signals, the kind of dynamics in the signal still look very similar, just that the artifacts have been subtracted. So you see that this low frequency, this really sort of low frequency drift is removed. But if you look at the higher frequency dynamics, they are not identical, of course, but they're very, very similar before and after removing the component. Okay, so then I don't actually save the EEG with the components removed. Instead, I save a list of components that I want to remove from each subject, and then I remove them prior to analyses. The reason why I do this, instead of saving the data with the components removed, is that once you have removed the components and then save the data, you can't unremove the components. You can't put the components back in. So if you change your mind later, or if you want to go back and say, well, I don't know about this component 24, maybe I want to leave that in. If you were to remove the components and then save the data right away, you would need to rerun the ICA from the beginning. But if you just mark these components to remove and don't remove them until you actually run the analysis, then it's much easier. You can just get rid of this number 24, and then you won't need to rerun the ICA algorithm. Okay, so now we get to see some of this in MATLAB. So I have some data loaded in here. So now I'm just going to illustrate a little bit of my approach for doing ICA cleaning. So we go plot and then component activations. And here we see the component activity. So I like to have this set up on the left. This is really a lot of personal preferences. So you should feel free to change this as you see fit. So here's a lot. This is all 65 components here. It's a bit too much to look at. So I do like maybe the first 20. And then let's see, set this to maybe 25. So now already this is interesting. You can see the first component is going to be the blinks. That's very clear. We can already see some things that look suspicious. So we know that these are ordered according to the amount of variance explained. And so 4, this line seems very flat relative to 3 and 5. So this already is a little bit suspicious. This suggests that there's going to be some big spikes later on. And here with 12 and 13, this also looks suspicious. We can see a lot of EMG activity, a lot of high frequency dynamics that are ongoing. And of course, these are trials, so we can scroll through the data and look and see what the components look like over time. So I have that, and then I go to Tools, Reject Data using ICA, Reject Components by Map. Now, as I said, I generally don't look at or don't consider removing components after the first 20 or 30 or so. So I generally will just plot the first 35 components because that all fits nicely into one figure. If you have more than 35 components, EEG Lab likes to open it up on multiple figures. Okay, so now you see each component here corresponds to each line here. So it's very clear that component 1 is the blink artifact. You see that here. You see also this very interior topography of the weights, so we can click on this guy. And that opens up this window that I showed earlier. So here, this is a longer experiment, but you can see where all these blinks are occurring around here. So mark this for rejection. It doesn't actually reject it from the data, it just marks it for rejection. So now it's interesting to look at some other components. We can look at component 2, just for curiosity and see what that looks like. It's a beautiful component. You see it's stimulus related and also response related. This is the in the experiment when there was another stimulus and then the subject had to indicate their response. So obviously you will definitely not want to remove this component from the data. This is a really clear task-related component. Here is this one, number 4. You can see that also looks suspicious here, right? Because the component is mainly driven by a single electrode. So that doesn't mean that I will remove it, but it does mean that I will, that I will sort of consider looking at it. So here we see, I mean, this is already very clear that you see there's a really clear ERP in this signal, so in this component. So there's a very strong task-related signal that's happening that this component is measuring. If you didn't have this vertical line here, you would know exactly where to put this vertical line because you see this ERP. So I definitely would not remove this component. So, you know, you can look through some other ones. I think these are often nice to look at. This one might be also related to the response. We can check out number 12. You can see this is suspicious because of the high frequency activity here. It's also suspicious because of the topographical distribution. It's mainly driven by one electrode and it's on the face. It's very interior. So yeah, this also looks like EMG artifact. We see here the power spectrum goes up again rather than sort of having this 1/f shape. The topography is on the face. When you look at this ERP, the single trial image, you can also see all this noise. And in fact, this is also kind of interesting. You see that it kind of comes and goes in bands, in waves, in blocks of time. So I guess maybe the subject was like scrunching his or her face or something, and then here they were more relaxed. Maybe they were very nervous about this experiment or something. So now, when you look at this time course, this is clearly very noisy time course, but there does actually seem to be a little bit of signal here. So I don't know I think I probably would remove this component anyway, but I don't think you would really need to remove this component, particularly, if you're focused on posterior activity, then you wouldn't necessarily need to worry about it too much, but I'll mark it for rejection for now. Let's see. So now I've marked a few components for, and you can go through these, and these are also components that are suspicious, but now these are getting to be pretty late, so I might not remove these. So we can go to Tools, Remove Components, and so in some versions of EEG Lab, I think there's a little bug here. You have to get rid of this. So here I say components to remove from the data 1 and 12. These are marked by default just because I already marked them here. Otherwise, you can manually enter more components. And here's the part where we say plot the single trials. And now we can see the data before and after the components have been removed. So the components have not yet actually been removed from the data. This is just showing what it would be before and after. So let's see, we'll plot some fewer channels just so we can look at it a bit more. Let's see, like this, and then guess you have to have a pretty good video card to have this stuff run quickly. So here you see this is super clear that we've removed a lot of the iBlink artifact here. The red line just sort of goes right along. And I think this component number 12 that I had removed also got rid of some of this noise here. So now if you want, you could go back and only remove component 1, the iBlink component, and not remove component 12, and then see how that looks, see if this decrease here really is due to the removal of component 12. Yeah, I think you get the idea. So let's see. I think that was it, and I believe that does it for the pre-processing lectures. So I hope you found these useful. Just to reiterate something that I've said repeatedly, but I think it's worth stressing, that pre-processing your data is something that tends to become an idiosyncratic procedure. And so the way that I pre-process my data that I've sort of discussed in these lectures is not necessarily going to be the best way to pre-process your data. So I hope you take this more as a source of inspiration for you to develop what you think is the best procedures for your data and your equipment and your experiments, rather than saying, well, Mike showed it like this, so it has to be like this. So don't think that. Anyway, I hope you found it useful.